So I guess the last time Masha talked about deep learning, introduced deep learning networks. Today we are going to talk about backpropagation, which is probably the most important thing in deep learning, like how do you compute a gradient and implement this algorithm. Of course, there are many other kind of like decisions you have to make in deep learning, and also they are like this kind of like backpropagation, this computing a gradient becomes kind of standardized these days. Like you don't necessarily have to implement your own like a gradient computation process where you can just all the gradient is done by the so-called auto differentiation algorithm. But this is actually the only algorithmic part in deep learning, so that's why we still teach it. And also in some sense it's still important because this idea of computing gradient automatically, actually has many implications in other areas. For example, suppose you want to study the so-called meta-learning. I'm not sure whether you heard of this word, like which is basically built upon this idea that you can do auto-differentiation for almost any computation you want. And this kind of same ideas also shows up in other cases. And also I know that some of the previous courses also covered the backpropagation. I think CS229 does cover backpropagation in some sense. So what I'm going to do is that, so in the past, like in the last 4 years, when I teach this, I have a lot of derivations, with all of these indices, and you compute the gradient of, you do the chain rule in a very detailed way. This year I'm going to try a slightly different approach where I'm going to make this a little bit kind of more packaged in some sense, like kind of divided into kind of like sub-modules. In some sense, it's a little more abstract. In some other senses, it's cleaner because you don't have to deal with all the small indices, like all the indices. Like sometimes there are 5 indices, like you have to keep track. And now everything is kind of in vector form. So and this is not like entirely new. It's not like I'm just doing an experiment because in the last time I did both of the 2 versions, right? I have the very fine-grained kind of like derivations and also have the vectorized form. And I think I got some feedback from you that the fine-grained derivation is not that useful because either you feel like it's kind of messy and I'm doing all of this computation like on the board and you kind of know how to do it and it's very messy, or if you haven't seen it before, it's kind of hard to follow, right? So if you haven't seen all of the like if you haven't seen kind of backpropagation at all, like even for a very, very simple case, and you want to do the very kind of like low-level stuff, probably take a look at lecture notes afterwards. It's kind of like independent. What I teach here doesn't depend on anything. It doesn't require any background, but it's more on the a little bit more abstract level to some extent. Like I would say it's more like on the vectorized level, so everything is treated as vectors. So if you want to do the more low-level details, you can take a look at the lecture notes, which I think that those part is a little easier and mostly covered by some of the other courses as well. So that's why I'm making this decision. Don't worry if you don't see any, like if my comments doesn't make sense here. Just if you haven't seen any backpropagation. So I hope at least this is still like a very the materials I'm going to cover today still is completely fine if you haven't seen anything about backpropagation. Okay, so let's get into the more details. So I guess so basically the so-called backpropagation. This is just a word that describes it's a terminology in some sense. Backprop that is a kind of a technique for us to compute a gradient of the loss function for a network. So recall that last time I think we talked about this. Like you have a loss function. For example, you have a loss function j of theta, which is maybe let's just look at one example, j subscript little j. This is the loss function of jth example, and this is something like yj minus h theta xj square, right? So this loss function can be other loss function. Here I'm just only using the square loss for simplicity. And this is a neural network. And recall that we talk about SGD, stochastic gradient descent. When you deal with neural networks, you always have to compute this gradient. So the algorithm is something like this, right? Minus alpha times j. The gradient of the loss function on some particular example, jk, maybe a random example, at the parameter theta. So basically today what we are going to do is that, so basically today, how to compute this. The gradient. So this is the main thing today. And once you know how to compute this gradient, you can implement this algorithm. And there's a generic way to compute the gradient. So what I'm going to do is that I'm going to start with a very generic theorem. And this theorem, I'm not going to prove it. You don't have to know how to prove it. But I think it's kind of good to know the existence of this theorem. So the theorem is saying that, I'm going to write down a statement, but the theorem is basically saying that if this loss function, j, by the way, I'm going to focus on only one particular example today, right? Because if you know how to compute a gradient for one example, then you know how to compute a gradient for all the examples. They're all the same. So the point is, and the theorem I'm going to write down today is that if you know how to compute the loss itself, like in an efficient way, then in almost all situations, you know how to compute the gradient of the loss, and in almost same amount of time. It's kind of like a very, in some sense, if you heard of it the first time, it's kind of a little bit striking. So let me write down the theorem. So I need to first specify some of the minor details, which don't matter that much. So anyway, this theorem is going to be stated somewhat informally. So let me define this so-called notion of differentiable circuits or differentiable networks. So and let's say this a differentiable circuits or differentiable networks are compositions of sequence of, let's say, arithmetic, am I spelling it correctly? Sorry, operations and elementary functions. By the way, my definition here is kind of like a little bit hand-wavy, as you can see, but the point is, you will see the point. The point is not exactly about the details, it's more about the form of the theorem. So by arithmetic operations, elementary functions, I kind of mean that, for example, things like, maybe addition, subtraction, product, division, and some of the elementary functions you can handle, actually most of the elementary functions you can handle. So maybe cosine, sine, so on and so forth. Right, exponential, logarithm, maybe ReLU, maybe sigmoid, there are many of these functions. Right. So, and suppose you have, this is my definition of differentiable circuits or differentiable networks. And you can see a neural network is often one of this, right? Because when you have a neural network, you have a lot of matrix multiplications, and it's really just, well, no matter how many matrix multiplications you have, it's really just some complex compositions of all of these, like operations, right? So in some sense, everything you compute, are some combinations of these things, right? No matter it's whether a neural network or something else. Okay, but I'm going to insist that they are differentiable because I'm going to I'm going to differentiate the output of this network. So here's my theorem. So maybe I should. I think the blue color is a little better, right? Is that right? Yeah. Okay. So and this is informally stated. It's not very far from the formal version. I guess just the formal version requires some minor details about the differentiability, so on and so forth. So the claim is that suppose you have a differentiable circuit of, say, size n. N means how many kind of like basic operations you are using. So this is my size. The size means the number of basic operations. And suppose this circuit computes of a real valued function. So I'm going to stress this. This is a real value function f that maps, let's say, L dimension to one dimension. I'm going to stress that this theorem only works when you have one output. So like the function can only have one output, but it can have multiple inputs. So then, suppose you have such a circuit, then the gradient of this function that you are computing, the gradient. So what is the gradient? The gradient at any point is a vector because you have RL out inputs, right? The gradient is L dimensional, right? So the gradient is an L dimensional vector. The gradient at a particular point, let's say x. X is just the abstract point. And this can be computed in time of n. I guess technically this is O of n plus d, but I guess sorry, I'm not sure why I'm on my notes. This is typo, I think. Oh, I see. So, okay, I guess time of n by a circuit of size of n. And here I have an implicit assumption because, implicitly assuming like n is bigger than d. Because if n is not less than d, it's a little bit, n is bigger than L. Because, if you have a circuit, the circuit, if it rate, most of the circuits should rate like all the inputs, right? So you probably need at least n L time to read all the inputs. So that's why I'm assuming n is bigger than L. If n is not bigger than L, then this has to be slightly changed, but the message doesn't change. So, okay, anyway, what's the main message? The main message is that if you can compute a function f by a circuit of size n, then its gradient can also be computed in a similar amount of time. And you just pay a constant factor more. And I think this constant is literally, in most of cases, this constant is just 1. Of course, when you really talk about the absolute constant, it has to depend on like how some of the small details, like how to really implement this, in the computer. So that's why I'm hiding the constant. But in some sense, you can view this constant as even 1. Okay, I guess, okay, sorry. I think whether the constant is 1, I think also depends on how do you count, right? So whether you assume you already compute the function f. So maybe, okay, so basically the constant would be 2 if you have to compute f and the gradient of f, right? So basically so if you know the function f already, then this constant would be 1. If you don't know the function f, then you have to first evaluate f and then do the gradient, and then this constant will be 2. I'll discuss this a little bit later as well. But anyway, for the moment, you can just think of that, you almost have the same amount of time. You can only use the same amount of time to compute the gradient. So gradient is never more difficult than computing the loss itself. So, and this is very general because it doesn't have to be a neural network, right? It could be almost anything like this. So, and if you want to, instantiate this theorem, for neural networks, of the loss of networks, then f, in this theorem would correspond to the loss function on a particular example, J's example, and theta is the variable x here, right? So, and the gradient of f corresponds to the gradient of the loss here, right? So, and what is L, right? So L is the number of inputs to this function f. So here, what is the input? What's the variable I care about? The variable I care about is the parameter theta. So L is going to corresponds to the number of parameters. And n, so what is the time to compute this loss function? The time to compute the loss function is kind of like the same as the number of parameters. So if you think about, you have a neural network of, 1,000,000 parameters, and how much time you have to use to compute the final loss function, right? You basically have to give your input to the network and go through the entire network and do all of these operations. And basically, eventually, the amount of time you have to spend is also similar to the number of parameters for evaluating the loss. Right? N is the time to evaluate the loss. So that means that the time for the gradient, so computing gradient, also takes, according to the theorem, this also takes O of n time. So basically, you only have to take O of number of parameters time to compute the gradient. Any questions so far?
Do you mind explaining why L is the number of parameters? Because it seems like L is the dimension of the input array, so they sound pretty different. Because like.
So here, that depends on how you map this apply this theorem to this setting. So here, I'm going to view this as a function of the parameters. So the parameter is my input to this function. I'm going to differentiate with respect to the inputs, right? So the theorem is a generic theorem, right? So like there is some function and you are differentiate with respect to input of the function, right? It depends on how you use this theorem. So if you use this theorem, you say the theta corresponds to the x there, right? So then what is L? L is the dimension of the x right there. So L is the dimension of the theta here. Yeah. Any other questions? Okay, so I guess the plan for the rest of the lecture is that we're going to show you how this works for neural networks. I'm not going to show you how this works for general circuits. It's actually not much more different if you do it for the general circuits, but it's just like the whole thing is you need to have a lot of jargon to really prove this with the general circuits, because you have to consider all the generalities, right? So basically, I'm going to show the concrete example for neural networks. How do you compute a gradient? And when you see the concrete examples for the neural networks, you kind of see how you do it for general circuits, which I will probably discuss, if I have time at the end. And another thing, like before I talk about the theorem here, I guess I'd like to say that this theorem is also the basis for many of the so-called second order method. So basis. And also, for example, for meta-learning. I guess we haven't introduced meta-learning, but I think the part that is kind of relevant is that I'm not going to talk about what meta-learning is in this course, just because it requires more kind of like backgrounds. But the general idea is that you can use this theorem twice, so that you can do something about the second order derivative. But there is a specific setting you can do. So basically, I think let me just give you a sense on what I mean here. This is not kind of like a comprehensive, because sometimes you're going to use this theorem in different ways, but this is one way to use this theorem in a clever way to get something more than what it offers. So for example, suppose in the same setting, you can claim that for any vector v of dimension L, this is the same as your input dimension of x, then this, the Hessian, the second order derivative, which is a matrix, this is a L by L matrix, times this vector v can be computed in O of n plus L time. And as I guess I said, n is kind of like bigger than L, so this is still kind of like n O of n time. So you can see that this is kind of like, now it's kind of a little more magical, right? Because if you want to compute this matrix, typically it takes, even just to memorize this matrix, right? Even you just want to kind of compute each entry, suppose each entry of this matrix takes O of 1 time, then you already spent L squared time to compute this matrix. So certainly, if you want to get O of n plus L time, your algorithm cannot just first compute this matrix and then to take the matrix vector product. That would be too inefficient, because just computing this matrix itself would take L squared time. So however, if you compute the whole thing without doing the matrix first and then take the matrix vector product, you compute the whole thing altogether, then there is a way to speed it up, and you can do it in O of n time. Well, n is bigger than L basically, right? So basically you just take O of n time.
If we can do that all of n time, why can't we just use like Newton's method instead?
Right. So Newton's method, depending on which Newton method you are talking about, the vanilla Newton's method requires this matrix. Then it's L squared time. So we only know how to do matrix vector, Hessian vector product. So that's why I think, at least there are a bunch of papers in the last few years which tries to implement the original Newton's method without computing the Hessian. So they try to use the Hessian vector product to have a different way to implement the original Newton's method. And that, was somewhat successful. I think you can have some algorithms that tries to only use the Hessian vector product to implement an approximate version of the Newton's method. Yeah, but it's not like it's not trivial. It's pretty non-trivial. Like you cannot do it just in the most trivial way. Right. So and actually this corollary is actually pretty easy to prove. And when you prove it, you can see how it's actually the proof also tells you how to implement this. So basically, the way to prove it is that you just say, I'm going to define a new function g of x. This new function is going to be the gradient times v. So this is a real valued function because this is a function that maps L-dimensional vector to a real vector. The output is a real vector, even though there's some. The output is a real valued scalar, right? Even though these are vectors, you take the inner product, it becomes scalar. And then, so if you use the theorem, so by the theorem, you know that g of x can be computed. In of n time. Just because the gradient can be computed, so that's why after you get the gradient, you take the inner product, you spend another of n plus L time, just to be precise. Because computing the gradient takes of n time, and then computing the inner product takes L time, you get of n plus L time. And then you use the theorem again. On G. So before you are using the theorem on F and you say the nabla F can be computed. Now you're going to use the theorem on G. So you view G as the new F, right? So you view the F as the, what's the right way to say it? So this G will be the F in the theorem, right? Then you verify whether G satisfies the condition. That's true because G can be computed in O of n plus L time. And then that means the nabla of G can also be computed in in O of n plus L time. Right, so this means that nabla G also can be computed in O of n plus L time. Because you can do this twice, right? And what is the nabla G? The gradient of G of x. If you do the computation, what's the gradient of this? It's really just you take another gradient here. I guess this probably requires a little bit, you can verify this, using chain rules offline. But then the gradient of G is really the gradient of the inner product of fx and v. And this is actually the Hessian of fx times v. Questions? And you can do this kind of things like for many other things where for example, if you define any functions of the gradient, you can still take the derivative, right? For example, I think in meta learning sometimes you have to have maybe some special function of the gradient. And then you have to take another gradient of it. And that's sometimes a sub-module used in meta-learning. And then you can apply this again, right? You can say, okay, this, because the gradient is computable in O of n time, this function probably is just a very simple function. So the whole thing can be computable in O of n time. And then you can take another derivative again. So that's when, I'm not going to go into more details, but that's how people are using it in meta-learning as well. So, okay, anyway, so this part is advanced material. We are not going to test it in any of the exams or homeworks, but just I feel like this is good to know to some extent, just because this is used in many other more advanced situations. Any questions? Okay, cool. So I guess now next, what I'm going to do is that I'm going to discuss a concrete case, right? A neural network. I'm going to start with two-layer network, and then I'm going to talk about deep neural nets. And basically, I'm going to apply the auto differentiation, right? The proof of the theorem is basically you have to give an auto differentiation algorithm, or so-called backpropagation. So basically, I'm going to apply the backpropagation to the specific instance, right, neural networks. Okay, so I guess let me set up some. So before talking about neural networks, maybe let me briefly discuss a preliminary. This is the chain rule. I'm somewhat assuming that this is covered in most of the calculus class, but I'm going to have to review this in here partly because I'm going to have potentially different notations from what not exactly the same notations from what you learn from the calculus class, just because different calculus book has different notations. So for the purpose of this course, what I'm going to do is that suppose I have suppose J is a function of theta 1 up to theta p. I'm trying to use as close notations as our final use case, even though this kind of like this part is supposed to be abstract, right? So all the notations are just some symbols, right? I'm trying to use similar notations just to avoid too many confusions. So suppose you have J is a function of a bunch of parameters, a bunch of variables. And then suppose you have some intermediate variables. Suppose there is a, okay, so how does this function work? This function works by I guess maybe, what is this function is defined in this following form. So you have some intermediate variables. So maybe let's say they are J1, which is a function of the inputs, theta 1 up to theta p, and also you have up to jk, which are some functions of this. So I guess I'm not sure whether this formula makes any sense. So I'm kind of using the ji as both the function and the variable of the output of the function. I think this is pretty kind of like typical in most of the math books, right? So you can view j as a variable, and then this j is a function of the theta 1 up to theta p, and which function it is, you still use j1 to describe that function. So does it make sense? Yeah. So and then just because I don't really necessarily care about exactly what the function is, so I'm just going to give a name, and this name is just called the same thing as the variable. So and then your j is a function of these intermediate variables. So and once you have this kind of like a two-layer setup, then suppose you care about the derivative. The chain rule is saying that if you care about the partial derivative of the final output with respect to some input theta I, then how do you compute this derivative? You can use the chain rule. So what you do is you say you are going to enumerate over all intermediate variables. So take the sum over j from 1 to k. And for each intermediate variables, you first compute the derivative with respect to intermediate variables. and then you multiply this derivative with the derivative of the intermediate variables with respect to the variables you care about, theta I. And just to clarify the dimension, so this is in R, and everything is a scalar so far. So, okay, so this is the chain rule, just in the language of this course. Any questions? Okay, so now I'm going to talk about a concrete case, and maybe let me also define some notations. So maybe one important thing to note is that every time, at least in the context of this course, every time you have this partial derivative thing, like we insist that this quantity, the quantity on the top, is a real valued function. So we are not considering anything about multi-valued outputs, not because you cannot consider them. It's more because typically in machine learning, if you are taking derivatives of a multi-output function, multi-variable function, computationally it's kind of like it's a problem. So in some sense, I think in machine learning people try to avoid that. Like at least on the algorithm level. Of course, in analysis, probably you have to think about that notion. But on the algorithm level, you always, like 90% of the time, you always try to take derivative of a real valued function. You never try to take derivatives of a multi-outputs, multi-variable functions. And in this course, we only have to think about the case where this is a real value function. So that's why in the notation, so the notation here is that, so suppose J is a real value function, valued variable or function, then of course it's kind of clear what this would mean, right? So if you take this with respect to some variable theta, that just means the partial derivative. That's easy. But what if you have a vector? So suppose if so this is easy. This is just so if theta is a real value vector, this is just the partial derivative, which is easy. And what if A is it the green one is not great? Maybe I'll use the black one. So if A is some variable in dimension D, then this would be also in dimension D. That's our notation. I'm just clarifying the dimensionality, right? So so basically this would be just a collection of scalars, the partial derivative of J with respect to A1 up to the partial derivative of J with respect to AD, which is dimension D. And we are also going to get into the situation where A is a matrix. Maybe A is a matrix of D1, D2. And now what does this notation mean becomes a little bit tricky, because sometimes in different literature there are a little bit different conventions. For this course, what we're going to do is just that this has the same shape as A. So this is also, this is just all the partial derivatives, and this is in the same as this, has exactly the same shape as A itself. So basically, in this course notation, this kind of derivatives or gradient, whatever you call it, right? So they always have the same shape as the original variable. All right. Okay. So I think I need to. Okay. So now let me talk about the two-layer network. This is just a review. I think Masha has talked about this. So, so you have something like, so if the loss function is evaluated by the following. So if you evaluate the loss function, what you have to do? you have to first compute the output of the model, and then you compare with the label, and you compute the loss, right? So basically, the computation to evaluate a loss function is the sequence of operations. So you first compute the so-called intermediate layers by doing something like this. This is the first layer weights times the input, the data, times plus some bias variables. And say, let's say this is of some dimension m. So, and then you apply some entry-wise ReLU. You still maintain the same dimension. And then you apply another layer. Maybe let's say another layer, let's call it O. The output of another layer is called O. So you apply W2A plus B2. And this layer, because this is the output layer, so you want to make this one-dimensional, so you get R1. And often, sometimes this is called H theta of X, right? This is the model output. And then you compute the loss. The loss is something like a half times Y minus O squared. By the way, I'm here only having one example, X and Y. X is the input, Y is the output. Right, okay, so that's just a quick review of the two-layer networks. I'm quite sure that we are using the same notation as Masha, hopefully. So, okay, so now the question is, how do I compute the gradient with respect to W, W1, W2, B1, B2, right?
This is not exactly calculated, but in general, how many of the samples will be using the gradient for all of them, or like will we just evaluate the gradient for a few samples, like in batch during this kind of model?
Right. So that's another layer, right? So that's that's about how you implement this algorithm, right? So if every time you just take one example, you just have to do it for one example. If every time you take a batch, then you have to do it for a batch. But for the purpose of this lecture, this is a good question. But for the purpose of this lecture, we only care about one example, because eventually you just do even you have like 10 examples, do all of them the same way. Yeah, you just repeat the calculation. Of course, you can parallelize all the gradients of all the examples, but the method is the same. So okay, so how do I compute the gradient of this, right? Like the gradient of the loss with respect to the parameters. So what I'm going to do is that I'm going to go ahead.
Sorry, just a question. Why is each data of x equal to 0?
Oh no, this is this is a variable called O. I think I probably should. I should change the notes. Yeah, like this is fine in the latex, right? Like, but how do I write this so that it's not look like a 0? I think it's okay to, let's see. So, is there any chance that I can do it on the fly to change the notation? I think I should be able to. What do you want me to change it to? Sigma is going to be used. It's going to be used for some other things. Tau, okay. But just this will introduce some inconsistency with the nodes, because in the nodes this is O. Just to let you know. Okay. But I probably should change that in the notes as well. Yeah, and also like you see that this one doesn't show up that often, hopefully. Okay, so what I'm going to do is that I'm going to try to use some chain rule with this, right? So how do you use chain rule? So for example, if you just look at one entry of this matrix, right? This is a matrix. You look at one entry. You can use the chain rule to derive the derivative of that entry. So that's the typical way that we do it. It's going to be a very complex formula, but you can still do it, right? So you use the chain rule multiple times, and then compute the derivative of that entry. And then eventually you get a lot of formulas, and then you try to regroup those formulas into a nice form. So that's actually written in the lecture notes. If you're interested, you can look at them. It's pretty much just brute force computation. Of course, if you do that brute force computation multiple times, then you get a little bit kind of like inspiration. You can do it faster in the future. So what I'm going to do is that I'm going to try to keep everything as a vectorized notation. And still I'm going to do chain rule, but I'm going to do a more kind of like a vectorized version of the chain rule. So because of that, I'm going to have this kind of abstraction. So this is, in some sense, I call this chain rule for matrix multiplication. I guess there's no unique name for this. This is just invented by me. But it's really a simple fact. So I'm going to suppose, so Z is equals to W times U plus B, where let's say, so W is a matrix of dimension, let's say M by D, and U is a vector of dimension D, and B is a vector of dimension M. You don't have to really necessarily care about the dimensions because at least as long as they match, then it's fine. So, and then I have some function applied on top of Z. So this is my abstraction, right? So you can see this is a little bit like this, right? Because if you map this Z to this Z, and this W1 to this W, and X to U, and B to B1 to B, then it's kind of like that. It's a kind of abstraction of a part of the problem. So, and then I'm going to claim that then the derivative with respect to the W, which is what I care about, at least if you map it back to here, we care about derivative with respect to W. So then this is going to be equals to what? It's going to equal to a derivative with respect to Z times U transpose. And maybe just to kind of like make sure you are convinced that the dimensions match. So this is supposed to be in R to the M by D because the derivative, as I said, should have the same dimension as the original variable W. So W is in M by D, then this is M by D. And this is in Rm because Z is an M-dimensional vector. So that's why this is in R. And this is in R1 times D, right? Because U is of dimension D and U transpose is of dimension 1 by D. I guess all the vectors are column vectors. So if it's R M-dimensional vector, it's really M by 1. So all the vectors in this course is column vectors. So that's why this whole thing kind of match the dimension, right? Because this is a column vector, this is a row vector. You take the outer product of them, you get a matrix. Actually, this is a rank 1 matrix. That's actually interesting observation. The gradient with respect to the weight matrix for one example is always a rank 1 matrix. Oh, but for one example, not for all the examples. Not for the full gradient. If you just have one example, the gradient for the weight matrix is typically a rank 1 matrix. And if you look at, and also we know the gradient with respect to B is going to be equal to the gradient with respect to Z. So this doesn't solve everything because you still don't know what this quantity is, right? This quantity is unknown here. And this quantity, the same quantity here is unknown. But at least it solves the local part, right? It's kind of like chain rule, right? It says that if you want to take the derivative with respect to W, then you only have to know the derivative with respect to intermediate variable Z. And then next I'm going to talk about how to take the derivative with respect to Z. So, but this is kind of a decomposition, right? So it says that if you want to know the derivative with respect to W, then you only have to know the derivative with respect to Z.
Can you explain again why you're putting in U transpose?
This is just what the formula tells me. But here I'm verifying that it does make sense because this is a 1 by D matrix, 1 by D vector or 1 by D matrix, and this is M-dimensional vector or M times 1 dimensional vector because I view all the vectors as column vectors. So that's why M by 1 times 1 by D will give you M by D. Now why is the transpose? That's just because the
matrix, you want the dimensions to match.
I think the fundamental reason is you do the calculation is exactly this, but it just happens to match. It has to match if the calculation is correct, right? Right. So and also maybe that's a reasonable way to memorize it. You have to make the dimension match, so that's why it's the case. So okay, how do you prove this? So Proving this, you have to go low level. You have to do it for every entry. So I'm going to show it at once, and then later I'm going to have more abstractions like this, and then I'm not going to prove it for you. So for this one, I'm going to do a quick proof. It's really just a derivation. So what you do is you just use the chain rule. So what you do is you look at the derivative with respect to any entry wij. So, and how do you do this? You say, you use the most basic version of the chain rule. You loop over all the possible intermediate variables. So what are the intermediate variables? These are z's, right? It sounds like it's very natural to use z as the intermediate variables. So I'm going to loop over all possible intermediate variables, k from 1 to m. And each of the zi is one of the intermediate variables, or zk. So dj over dzk, and then dzk over dwij. Right? And then I'm going to plug in the definition of zk. So then this, what's the definition of zk? Zk is this is defined by this matrix specification. What is the case dimension of here? It's the case dimension of this. The case dimension of this is going to be something like the definition of matrix specification, wk1 times u1 plus wk2 times u2 up dot dot until wkd times ud plus this b, the bk. And you look at the partial derivative of this with respect to wij. So how to do this is kind of like, so first one, to make this non-zero, you have to make sure that this variable at least show up in the top. Right? If the variable doesn't even show up on the top, there's no partial derivative. The partial derivative will be 0. So this is only non-zero only if this wij does show up in the top. So when wij shows up on the top, only if k is equal to I, right? So that because only wk something show up on the top, and wij, so only I and j are the same, I and k are same, then wij can show up on the top. So that's why you only have to care about those cases where k is equal to I. So you just the entire sum is gone, so you only have to care about zi, and then. So you have, maybe like, I'll just do it slowly. So this is just wi1 times u1 plus up to wid times ud plus bi over dwij. Okay, so wij only show up once here on the top, linearly. So wij show up here on the top in this term somewhere in the middle, right? So there's a middle term which is look like wij times uj. That's the term that where wij shows up. And the derivative of this with respect to wij is equal to uj. So that's why this is equal to, times uj. Right. So that's my dj over dwij. And then I have to group all of this into a matrix form. So if you verify that, so basically you group all of these entries into a matrix form, it will be like this. So you're going to get all of this dj over dzi into this dj over dz term, and then this uj term will be grouped into this u transpose. So I guess I'm using a very simple fact. The simple fact is that if something, maybe let's say xij is equals to ai times bj, then this matrix X is equals to A times B transpose. That's the simple fact I'm using, right? So if the entry of a matrix is equal to some AI times Bj, then you can write it as matrix form, where this matrix X is equal to A times B transpose. A is a vector, B is a vector. Any questions? Okay, so now I'm going to apply this abstraction, this so-called vectorized form of the chain rule, to a problem here. So what I got is that, so what's the mapping? The mapping is that Z maps to Z, and the W1 maps to W, X maps to U, right? And J maps to J. So that's how I use this abstraction. So, and after I use this abstraction, what I got is that I get W1 dj over dW1 is equals to dj over dz times U transpose will be X transpose, X transpose. Okay, so of course this is not done, right? Because we want to compute this, but we kind of like we have a reduction in some sense. So we did some partial work, right? Our goal is to compute this, but now we said that you only have to compute this, dj over dz. And next I'm going to show you how to compute dj over dz. So it's kind of like you are kind of peeling off a layer by layer in some sense. Of course, you can also do the same thing for B. I guess the B is always easier, so this will be just this. Okay, so next question is how do you do the let's see whether maybe I should use a new board. So next, I'm going to compute this, right? The Z is this Z. So how do I do this? I'm going to have another abstraction. So this is an abstract problem. So note that my Z, the relationship between J and Z is through this A and W2, right? So there's some complicated dependencies between J and Z, right? So I'm going to abstract one part of it just to make our kind of derivation clean. So the abstraction would be that you think of suppose you have a variable A which is sigma of Z, and then J is a function of A. So and sigma is this entry-wise. Sigma is entry-wise kind of like a activation function. Right, sigma is the value basically. So I'm going to claim that in this case, you know that your target, the question you care about, dj over dz, is going to be equals to dj over dA times sigma prime z. And this is so I guess let me explain the notation here. So this is our m-dimensional vector. This is also m-dimensional vector. Let's say in this abstraction Z, A, they are all m-dimensional vector. So then these are all m-dimensional vector, and this is the so-called entry-wise product. Right, so I'm taking two m-dimensional vectors, I take an entry-wise product, and I get the derivative I care about. So, okay, and then you can see that the only thing you have to compute next is what is dj over dA, right? Because dj over dA is still unknown. I'm not going to do this proof for this. It's actually even easier than the other one. You just have to expand and do the chain rule. Okay, so now next let me try to so now I'm trying to deal with dj over dA. So how do I deal with dj over dA? I'm going to, again, abstractify this part of computation in some abstractive form. So my abstraction is that, so the abstraction is that, I guess I'm going to have A is equals to W times U plus B, and J is equals to a function of A, right? So why this is a reasonable abstraction? Because A maps to this A, W maps to this W2, and this U maps to, wait, am I doing something? Sorry, my bad. I have to use a different, okay. Maybe let's call this tau. Okay, that's a perfect place to call it. Okay, so tau, okay, so why this is a useful abstraction? This is because the mapping in my mind is that tau means the tau above, and the W here means the W2 above. And B here means the B2 above, and J means the J. So note that the difference here is that this W now means the second layer. Right. So, and if you make this mapping, right, so then what you care about is that you care about dj over du here, because u, oh, I guess I didn't say what u corresponds to. So u corresponds to A. Right, so u corresponds to A, because A is what is multiplied with the matrix, right? So dj over du, so that's what I care about. So you can see that even though this abstraction is very similar to this abstraction, the difference is that here I care about dj over du. I care about the derivative with respect to the input of the matrix multiplication. And before I care about the derivative with respect to the matrices, the matrix in the matrix multiplication. So, right, so that's why it's a little bit different. And you're going to have a different formula for it, of course, because you are taking derivative with respect to, one is with respect to W and the other is with respect to U. Right. So, okay, so what's the formula for this? The formula for this is if you write it in the matrix form, it's W transpose times dj over tau. So I guess if you check the dimensionality, then this one, okay, I don't know what the dimension here, so I guess let me specify the dimension. So say W is maybe something like, I don't know, let me come up with the maybe R times M, right? So and U is of dimension M, and tau then has to be in dimension M, so dimension R, sorry. So then this is in dimension R. And this W transpose is in dimension M by R. And that's why they can be multiplied together. Of course, okay, I guess another thing is that if you don't want to remember all of these equations, if you want to remember this, so first of all, you don't have to remember all of them. Second, if you want to remember them and you want to kind of cheat a little bit, you can just view them as scalars. And you can see then, so for example, this one would make a lot of sense if they are scalars, right? That's just the trivial chain rule. And this one makes a lot of sense if they are all scalars, because if you want to take the derivative with respect to u, then w have to show up as the coefficient. So everything makes a lot of sense if they are scalars. And the only tricky thing is that if they are matrices, then you have to figure out what's the right transpose. If you left multiply, right multiply, so on and so forth. Okay, so Okay, so once I have this thing, then I can apply this to the special case above. Right? If you apply it, then what you get is that with this mapping, then you get dj over dA is equals to W2 transpose times dj over d tau. Right. That's because, right, I'm just replacing the notation. I'm just applying this general thing to this case. And now you see that there's only one thing that is missing, which is dj over d tau. And that's trivial, right? Because dj over d tau is just, this is really just the very last thing. J is just the y minus tau square. So dj over d tau, like everyone can compute. This is just, I think, minus y minus tau. So what you really do, eventually, then what you really do eventually is that you first compute this. Maybe this is step 1. And then this is step 2. You compute dj over dA. Then where dj over dA is used, and then dj over dA is used here. So then you do this step 3. And then you get dj over dz. dj over dz, then you used it here. This is 4. Wait, maybe 4 is here. Then you get the derivative with respect to W1. So when you really implement it, you have to do it backward. When you do the derivation, it's reasonable. We can do anyway, but I guess I'm doing it in this way, from the lower layer to the top layer. Sorry, from the first layer to the second layer. But when you really do the implementation, you have to first compute this and this and 1, 2, 3, 4. I guess I didn't compute the derivative with respect to all the parameters. So I only compute the derivative with respect to W1 and B1. What if you want to compute the derivative with respect to W2? Maybe that's a good question to see whether it somehow digests this. What if you want to do the dj over dW2?
The chain rule considers the derivative with respect to 12, and then times the derivative of tau with respect to W2. And
so, and for example, which abstraction you're going to use? Like I have 3 things, right? 1, 2, and 3. Which one are you going to use? Yeah. But I think your answer is correct. So I guess I think you're going to use this because W2 is the matrix, right? You care about derivative with respect to the matrix, then you want to use this. So basically, so if you care about this, then you view this W2 is the W here. So I guess then you need a different mapping. So I guess you need to use the first abstraction, the first lemma. And then you're going to say W2 corresponds to a W. And the U now corresponds to what? U corresponds to the A here. And B1, B2 corresponds to the B, and Z corresponds to, sorry, not Z. So the tau corresponds to Z. So this is in the right-hand side is in the abstraction, and the left-hand side is in the real case I care about. So this means that this is dj over d tau times. I had U transpose here, now I had A transpose here. So I'm going to have A transpose here. And I also know dj over dB2 is going to be equals to dj over d tau. Make sense? Okay, so now if you have all of this, then how do we, I guess this is still a little bit complicated, right? So, but it's a little bit better than before because everything is vectorized notation. And now, what if you do it for multiple layers? You'll see that everything is just the same. So you basically just going to repeatedly use these two lemmas, or the three lemmas, or three abstractions. I guess maybe I should number them in some way. Maybe let's call this lemma 1. And then here I'm using lemma 1. And maybe let's call this lemma 2. And this is lemma 3. So I'm going to, for the deep networks, I'm just going to use lemma 1, 2, 3 repeatedly, and I'm going to get the gradient. So that's the last thing in this lecture. So let me first recall the deep networks. So suppose you have multiple layers of networks, so then I guess using the same notation as last lecture, the first layer is this. The second layer is some ReLU times Z1. Sorry, this is still the first layer. This is the activation. And then you do the second layer. You have W2, A1, plus B2, dot, dot. Then you get the R minus 1 layer, which is ReLU of Z R minus 1. And then let's say you have the rth layer, ZR, which is equals to WR times AR minus 1 plus BR. And then finally you have a loss. I guess I'll just write the loss here. Given it, the loss will be, J will be a half times Y minus ZR squared. Okay, so that's my computation of the loss function. A sequence of matrix multiplication and the activation functions. So now I'm going to try to compute the derivatives, the partial gradient. So first of all, I'm going to compute dj over dwk for some kth layer. So how do you do that? Yeah, this is a little bit awkward. I guess maybe it's okay to, you all know this is deep nets, right? So, is it better? Yeah, nothing different. This is the same thing as in last time. I'm just recalling the notations. So, and I want to compute a derivative with respect to kth matrix. So maybe let's say a derivative with respect to W2, let's say. Right? So suppose K is 2. Then how do you do it? So if I want to do this with respect to W2, then the thing is that you want to use the lemma, right? So the lemma 1, I guess. Maybe that's the most relevant because lemma 1 is trying to take derivative with respect to some W. So you just do some pattern matching. You want to apply lemma 1. So what's the abstraction here? The abstraction here is that if you okay, so how do you do the pattern matching? So I guess you say that what's the definition of WK? WK is involved in this computation in the following way. So WK is involved in the following way. ZK is equal to WK times AK minus 1 plus BK. This is how WK is involved. And then you say, I don't care about what happens next. I just abstractify the rest. So then this is pretty much the same as the setting in lemma 1. Right? So then using lemma 1, or you can, using this, actually you can call it, you don't have to call it lemma, you can call it a formula or something. Right? So lemma 1 tells you that if you take the derivative with respect to the matrix, it's equals to the derivatives with respect to zk. Zk is basically the output of the matrix multiplication. So times the input of the matrix multiplication, which is AK minus 1 here, transpose. Okay. So that means that I only have to take the derivative with respect to zk. Right? Zk is basically some of these intermediate variables. Right? So how do you take derivative with respect to zk? So you need to think about how zk is involved in this computation. Right? So zk is involved. So I care about this. And zk is involved in the following way. I'm not sure. So zk is equals to ReLU. Okay, sorry. Zk is involved directly in the following way. So ak is equals to ReLU of zk. And then j, the loss, is a function of ak. Right? That's the part that zk is directly involved. Because you first go to the ReLU, you get A, and then you do some computation to get J. And then you can use the so-called lemma 2. So the lemma 2 will tell you that what is the dj over dzk. So it's going to be something about dj over dak times the ReLU prime times of zk. Right, this is lemma 2. And the third thing is how do you deal with AK? Right? What is the derivative with respect to AK? So if you don't know derivative with respect to AK, then you have to see how AK is involved in this whole computation. So how is AK involved? So AK is involved because AK, if you're going to use A to compute Z again, use A to compute ZK plus 1. Right? So if you look at that part, so basically ZK plus 1 is equals to some WK plus 1 times AK plus BK plus 1. This is the first time AK is used and the only time AK is used. And then you say the rest of the thing is abstracted as a general thing. And then you say I'm going to use, now I'm going to use lemma 3. Because lemma 3 is also about matrix multiplication, right? Lemma 3 is also about matrix multiplication, but it's trying to take the derivative with respect to the input to the matrix multiplication. Right? So A is the input, right? So So using lemma 3, I'm going to say, I guess maybe, I'm not sure whether I should also make an explicit map. So if you care about the explicit map, then it means that AK corresponds to the U there in lemma 3. Right, so WK plus 1 corresponds to the W there, and BK plus 1 corresponds to the B there, and J corresponds to J. I guess ZK plus 1 corresponds to tau. Right, so I guess if you keep pattern matching, I think it's a little bit difficult to see the map. Probably the right way to think about it is that you think about the rows of these things, right? So ZK plus 1 is the output of the matrix multiplication. AK is the input to the matrix multiplication, and WK is the matrix in the multiplication. So that's how you easily map the rows of them. And then so you get this thing is equals to WK plus 1 transpose. So, and then, oh, sorry, I think I have some, this should be Z. So then you can see that if you look at this two, sorry, this is bilemma 3. So if you look at this formula and this formula, basically this is kind of like a recursion in some sense, right? So here you are saying that from dj dak you can compute dj zk, and here from basically you can just recursively use these two to get all of them. So I'll just make it explicit. So so basically, with all of this formula, you already compute everything. It's just I'm going to reorganize this to make it a little bit clearer. So what you do is that you start from the last layer here. So you first compute, I guess, maybe let me just describe the final algorithm. So you first compute the so-called forward path. So you compute all the values of all the variables. So in some sense, I've already assumed that it's computed implicitly before. So basically compute all the Z1, A1, Z2, A2, so on and so forth. Right? So just by computing all of this network, evaluating the loss, you get everything. Right? So you get all the variables. And then in the so-called backward path, you compute the gradient. So, and the way you do it is that pretty much like same as the two-layer network, you start with the last one. So you first can compute this with the last layer. And this is trivial because J depends on ZR just in a very trivial way. So this is just the minus Y minus ZR. Right. So this is our starting point. And now you recursively use both of this to get all of the dz of dz over dA. So you already have dj over dz, dj over dzr, and then you can use that to compute the previous one using this, right? So from this you can get dj over dar minus 1 using this formula, because you get this is w. if I can do it on the fly correctly, I guess this is AR transpose DJ of D ZR. Right, so you remove the index by 1, and you get to A. And then you can use the A to compute the Z, the dz over dA to compute the dz over dj over dz. So this is number 1, this is number 2, number 3. You get ZR minus 1, which is equals to R minus 1. Right. So basically, after doing this iteration, you get from R to R minus 1, and then you repeat. Right. So then you can repeat. You can say, I guess maybe I shouldn't number them by. So maybe I should number this one by 1. This is 2, 2.1, 2.2, 3.1. In the third round, you get AR minus 2 using this equation. Maybe let's say this equation, let's call it 2. Let's call this 1. So this is using 2. And then you get the Z version using 1. And you do this repeatedly. So you get everything about A and Z. And after you get everything about A and Z, so basically after obtaining all the everything like this, it's pretty easy to get the gradient with respect to W, because you can just say is using this. Maybe let's call this 3. You can say this is equals to okay. So I guess you can see that I do need a forward pass, because in my backward pass, I do require a bunch of quantities. For example, it does require, I know the quantity Z, R minus 1. So I have to save all the easy quantities, A and R, all of this in my memory. And then in the backward pass, I'm going to use them. And why this is called backward pass? In some sense, if you think about the computational flow, I guess this is probably my last point that I can make today. So this is kind of like it's the reason why it's called backpropagation is because you can view this as, you can see that the way that you change the index is you start from R and R minus 1, and then you do R minus 2, R minus 3. So you do this in a kind of a backward way. So in some sense, if you kind of draw a kind of a computational graph or kind of a flow of the computation, I'm not being very formal here, but if you draw it in some sense, then you can view this whole computation as you start with X, and then you have some matrix multiplication. You need to use the weight W1 and B1, and you do some matrix multiplication, and you get Z1, right? And then you do another matrix multiplication. Maybe you do another A. Maybe this is let's say you get Z1, and you get the activation. Say activation, and you get A1, and then you do a matrix multiplication with also W2, B2, and then you get Z2. And you do this repeatedly until finally you get ZR, and then you get the loss J. Okay, so this is kind of like the forward pass. And if you think about how to kind of like conceptually how do you organize the information in this backward algorithm, in some sense what you do is that I'm just trying to visualize this, but of course all of this will be in computer. So in some sense what you do is that you first compute the derivative with respect to this variable, ZR. Okay? And then you say, okay, how did you get the Z? You get the Z by some matrix multiplication, right? So let me say this is by some matrix multiplication, where the input of this is AR minus 1. Right? So and so then you take this in some sense from this you compute the derivative with respect to AN minus 1. Right, that's my step 2.1. Right, and then you just keep doing this in a backward fashion. So you figure out where A come from, AR minus 1 come from, AR minus 1 come from ZR minus 1. So that's why you do a backward pass. You say this is computed from N minus 1. Right, that's my step 2. Okay, sorry, I'm not numbering this correctly. So this is 2.2. That's my step 2.2. Right, so, and I keep doing this. Eventually I get maybe Z1. Right. So that's the so-called backpropagation in some sense. And in the middle, you can also compute the derivative with respect to the W. So because the derivative with respect to W is equals to something about the derivative with respect to Z. So basically, once you get this quantity, you can start from this quantity to get the derivative with respect to W R minus 1, I think. R minus 1 or R minus 1. And then, every time you get one more dj over dz, then you can get one more dj over dw. So from this, you can get dj over dw1. So that's why it's called backpropagation. And maybe just to say one, I know we are running out of time, just one more word about this. So this is a kind of very sequential computational graph. But actually, if you have like a more complex computational graph, right, so which is not like as sequential as this, you can do almost the same thing. Basically, you just write out this graph, and then you figure out how to do the backpropagation. And the way to do the general way to do the backpropagation is exactly the same. You just run in the graph in the backward. The only thing you have to figure out is that how does this like what's this relationship? Basically, this arrow, right? So how does the derivative with respect to A depends on Z, right? So what's the derivative with respect to the input of this module, you view this matrix multiplication as a generic module, let's say, right? So, and the only thing you have to figure out is that how do you write this so-called backward function? This backward function takes in the derivative with respect to the output of this module, and output the derivative with respect to input of this module. And that's the so-called backward function. For example, if you write PyTorch, if you need to write a new module, basically you have to implement the forward function and the backward function. The forward function is how do you get Z from A, and the backward function is how do you get the derivative with respect to A given a hypothetical derivative with respect to Z. By hypothetical, I mean like just some vectors, right? You take in some vectors and you get some vectors out. And this is the function you have to implement for the module. And once you have this module, then you can run like then you just everything else is systematic. Yeah, I think we should stop here. Okay, thanks.